In this video, we are going to discuss the concept of stress elements. Stress elements are a useful way to describe the stresses that act at a specific point in a body. Oftentimes, an engineer needs to describe the stresses that occur at a certain location in a machine component. And using the concept of a stress element, the engineer is able to do that. To define a stress element, the first thing we do is draw a representation of a three-dimensional stress element. We define a right-handed coordinate system with x going in the right direction, y positive going up, and z positive coming out of the page. This makes a right-handed coordinate system in that we can put our fingers in the x direction, wrap them to y, and have a positive z. This is a three-dimensional stress element. To define the stresses here, we would define our normal stresses perpendicular to the face of interest. So for example, this would be a sigma x stress because it's normal to this x face. This stress here acting on the z face would be a sigma z, normal to the z face, and we'd also have a sigma y acting normal to the y face. The shear stresses are defined using taus, and they occur in the plane. The shear stress acting on the x face in the z direction would be defined as tau x face z direction. And note that this tau is in the x plane and acting in the positive z direction. In order to keep our system in equilibrium, we have to have a tau acting on the z face now in the x direction. So this shear stress here would be equal to tau z face x direction. And we know that in order to have this system in equilibrium, tau xz must equal tau zx in magnitude. The remaining shear stresses would be tau x face y direction, tau y face x direction, and again tau yx would be equal in magnitude to tau xy. The final shear stresses we would have would be tau on the y face in the z direction, and that would be equal in magnitude to tau z face y direction. This is the definition of the stresses in a full three-dimensional stress element. It doesn't get any more complicated than that. Oftentimes we have a plane stress situation. In plane stress we have stresses in one of the normal directions goes to zero. So we have sigma z, for example, would equal 0. And any other stresses that have z components in them would also equal 0, which implies tau zx and tau zy. And if zx is equal to 0, xz also has to be equal to 0. And if zy, tau zy equals 0, tau yz also equals 0. So in this case we would have tau zx equals tau xz equals tau zy equals tau yz, and all of those equal 0. When we do that, this three-dimensional stress element will reduce to a two-dimensional stress element. So if sigma z goes to 0, tau zx goes to 0, tau xz goes to 0, zy goes to 0, and yz goes to 0, it can be seen that we are left with a stress element that is two-dimensional. Looking into the z direction, we would have a sigma x acting in that direction, a sigma y acting in this vertical direction, and the only shear stress we would have would be tau x y, and on this plane tau y x. And once we draw these stresses in these directions, we know these shear stresses must act to keep the system in equilibrium. And we have now taken this three-dimensional stress element here that is relatively complicated to a simple plane stress element where the full element consists of two normal stresses and essentially one shear stress. Plane stress elements occur in many locations, and in particular many beam configurations and loadings consist of plane stress conditions. For example, if we have a cantilever beam like this square cantilever beam here that would be fixed on this end, we apply a load in this direction and we apply a load in this direction, and also a torque on the end of this beam. A stress element back here at the top of this beam would be in a plane stress configuration, in that there would be no stress in the z direction, and we could draw that stress element as a simple two-dimensional plane stress element. We would have stresses acting in these directions, we would have stresses acting in these directions, and we'd also have shear. Now it's important to note then that this, although I have drawn this with some size to it, it represents an infinitesimally small element that occurs exactly at that point. The same thing with the circular cross-section. If we put loads on our circular cross-section like this, we could look at stress elements back here on the top of the beam that would have plane stress, a plane stress state, and we could also look at stresses on an element that occurs here on the side of the beam that would also be in a plane stress type situation. So again, to summarize, a plane stress element is a two-dimensional stress element that is infinitesimally small, but we draw with a finite size such that it is easy for us to understand the stress vectors that act on that particular stress element. If I were to look at the ends of these beams directly on, for example, the stress element represented by this top stress element here would be an infinitesimally small point, but I will actually draw the element with a finite size, and it would look something like that. My stress element on the side again would represent an infinitesimally small point, and I would draw it with a finite size that would look something like that. Then when I come over and add the stresses to these elements, depending on the loads, I would have stress vectors that were going in their given directions. And using this approach of stress elements greatly simplifies the ability to describe the stresses that occur at a specific point in a loaded structural body. I hope this video has helped clear up some of these issues.